Let's take a look at this problem together and see if we can make some sense out of it. It does have some little tricks to it. It's a kinematic problem that deals in 2 dimensions, so we have to take into account both dimensions to solve this. So let's take a look and see what's going on. It says an airplane shown is flying in level flight at an altitude of 0.5 kilometers at a speed of 150 kilometers an hour. At what distance d should we release a heavy bomb to hit the target x? Take g to be 10 meters per second squared. Well, after I read the problem, I want to draw a picture. There's a few things that I don't like about this problem that make me want to just start changing what the picture is. And the first one is I don't like the 0.5 kilometers. I like 500 meters instead. I also don't like the 150 kilometers an hour. I know that there's 150 kilometers an hour. I know that in 1 hour there are 3,600 seconds, 60 minutes in an hour and 60 seconds in a minute. So 3,600 seconds in 1 hour. And I know that there's 1,000 meters per kilometer, which gives me somewhere around 42 meters per second. All right, so I have my picture. I read the question. I'm going to draw a coordinate system. I'm going to say this point right here, this point right there is where 0, 0 is, and this is my positive x-axis, and this is my positive y-axis. Now, when I go through this problem, I can't change this coordinate because it's set. So let's look and see what some of our initial values are. I'm going to do my original position. My original position, x naught, it's a vector. It looks like an x. It looks like I'm just dealing with the x coordinate, but it is a vector, so I have 2 pieces for it. I see that it is in 0 in the x direction, and I see that it's 500 meters in the y direction. So my vector looks like this. My original velocity, I can say, is 42 meters per second in the x direction. And since it's not going up, it's in level flight, 0 in the y direction. My acceleration, this is actually a pretty easy one. Nothing in the horizontal direction. And minus 10 meters per second squared in the y direction. G is a value of 10 meters per second squared, but I know G points in the downward direction, which is opposite of what my coordinate is. And last but not least, I'm going to look for my final position. And this is the one I actually really don't know. This is going to be d in the x direction. Start at 0, I go a distance d, so this is the value I want to find. And when I'm at the end, this bomb has tracked all the way down to the bottom, and it ends up at 0 height, so 0 in the y direction. All right, I look at these equations and I go, well, I have initial, final positions, I have initial velocities, I have accelerations. My acceleration is constant. It makes me really want to use the equation x equals x naught plus v naught t plus 1/2 a t squared. This is the full vector equation. Let's box in my known values. So this is the full vector equation, and I'm going to have to deal with these each part individually. Well, a lot of these problems solve with the height difference is going to be what gives us our time. So I'm going to solve our y position first. I'm going to choose a different color for this, just because I can. So in the y direction, y is equal to y naught plus v naught y t plus 1/2 a y t squared. And notice this is no longer a vector equation. It's just scalar values. I have my values over here. As long as I'm using my y coordinates, I'm going to be okay. So I'm going to go through my original y position, or my final y position is 0. My original y position is y naught. My original y velocity is 0, and my original y acceleration term is 1/2 gt squared, and g is a value of 10, and it's in the minus direction. So I started to substitute in. I didn't do a full substitution in because I'm going to rearrange this equation first. And I'm going to find that when I rearrange this equation, I get y naught on the other side. The minus sign will drop. Really, I'm moving the 1/2 gt squared to the other side. I get a value of 2, and I have to divide by g, and this is going to give me t squared. Well, I don't want t squared, I actually want the square root of t. So I'm skipping a few steps in here, but you can just do some basic algebra to get to this value, which, if we substitute things in, 2 times 500 meters divided by 10 meters per second squared, all square rooted, gives me a value of 10 seconds. So I get a value of 10 seconds. That's how long it takes the bomb to go from the plane to the ground. And one thing I didn't mention was that because the plane and the bomb are connected to begin with, we're going to assume that they're going to have the same initial velocity. All right. Let's go to the x direction. We have x is equal to x naught plus v naught xt plus 1/2 axt squared. Same equation as this, just looking at the x components. Make some substitutions in. I start with d is where I'm going to end up. I'm going to end up at a distance d from my origin. I start at initial position of 0 in the x direction. I have initial v naught x at the beginning, and last but not least, I have 0 at the end. So d, 0 acceleration, that is. D is equal to v naught x times t. V naught x is 42 meters per second, and t is 10 seconds. So at the very end, when everything is said and done, this is approximately 42 or 420 meters. The seconds cancel out. So I look over at my equation, and I see that the value of c is the one that solves this equation. So just to give you a full view of how everything works out, we solve the y direction to give us our time. We use that time value to go through and substitute in our x equation. Our x equation gave us our distance. But we really were careful at watching our unit conversions at the beginning and making sure we write down exactly what each of the y and x coordinates are for position, velocity, acceleration.